Okay, welcome everyone to this continuation of what is tropical geometry. Today I would like to tell you about polyhedral geometry, because tropical geometry and polyhedral geometry, well, they're not the same, but they are very, very closely related. And by polyhedral geometry, I mean kind of the science of polyhedron. So let's see what a polyhedron is, in case you don't know what a polyhedron is. Polyhedron. I hope I will find a nice picture. Yeah, those guys here, right? So, yeah, let's have a look at some images. Yeah, those guys. Everyone has seen a polyhedron at one point in your life. Whatever. Platonic solid, but not necessarily just a platonic solid. Here's a platonic solid. Again, the platonic solids. Who doesn't like the platonic solids? More platonic solids. The 5 platonic solids. So it's almost all about platonic solids, apparently. But it doesn't have to be about platonic solids. So everything that looks like a platonic solid, that's essentially a polyhedron. And why is this related? You might wonder. Well, the Newton polygon, which I will recall for you, is essentially the polyhedron that determines the tropical varieties. Okay, so that's like the relationship between the two. So whenever I say polyhedron, as I said, you should think platonic solids and friends. Platonic solids and friends. Very, very difficult. Okay, so the first starting point of polyhedral geometry is the notion of a convex hull. Yeah? Convex hull means, so convex means whenever you have 2 points, well, here, so convex, so the blue thing here is convex, and here I have 2 points, and then the line between them is also in the set, right? You have 2 points in the set, and the line between them is in the set. So this is convex. Something like that, a peanut type shape, wouldn't be convex because, well, you have 2 points here, but the line is not in the set, right? Okay, and the first observation is this convex hull of a point cloud, here a lot of points, is usually a polyhedron. There we go. This is kind of one of the first notions in polyhedron geometry, and tropical geometry, recall tropical geometry is this piecewise linear thing. So it's crucially related to polyhedrons, which are really, let me pull up the pictures, like this piecewise linear, so it's linear here, but it's not quite linear. Linear would be a bit too boring. Those piecewise linear objects. So that's kind of a starting point. Convex hull, polyhedral geometry, tropical geometry, right? And here's a better picture of a polyhedron, which is not quite a platonic solid, but it's almost as a platonic solid, whatever. A polytop. So a polyhedron, by the way, doesn't need to be bounded. A polytop would be something bounded. But anyway, a polyhedron is some intersection of many closed half spaces. Yeah? So this is an example of a polyhedron. So you have, it's essentially saying it's piecewise linear. But it's not, and so it's given by an inequality like this, where A is some matrix, right? And B is some vector for the, well, it's a set of linear inequalities, right? It's not equalities, that would be boring, it's inequalities. And then you get a polyhedron. And as I said again, it's a very piecewise linear object. Doesn't necessarily need to be bounded. If it's bounded, people call it a polytop. So let's see whether we can figure out the difference between a polytop and a polyhedron. And it looks exactly the same, right? So this is a good example here. Convex polytop, another polytop, whatever that thing is, a lot of polytops. This is a polytop, whatever. You know what a polytop is by now. Polyhedron, unbounded polyhedron. Polyhedron. Something like that could also be a polyhedron, right? So it's fine. So polytops really like platonic solids, and polyhedron could be something unbounded, right? It's still given by a bunch of linear inequalities. Hope that makes some sense, right? So this is polyhedron, and otherwise a polytop, right? Bounded polytop, bounded polyhedron. This thing here, for example. And what people usually then do is they glue them together, and it's called a polyhedral complex. So here, certain crystals and whatever, they tend to be polyhedral complexes. Don't worry too much that this is not really a polyhedral complex. I'll let you figure out why. But in math, we give it 2 conditions. So it's a collection of polyhedra. Yeah, that's what it's supposed to be, a polyhedral complex, something like that. The picture is actually really good. Some crystal type picture like that. So up to 2 conditions, like the intersection is in both of them or something like that, right? So it's not a completely random collection of polyhedron, but it's a reasonably nice collection of polyhedron. But anyway, so these are kind of the classical notions of polyhedral geometry: convex hull, polyhedron, and I really just need the polyhedron to define a polyhedral complex. Polyhedral complex, a collection of polyhedra. Okay, so why am I telling you this? Except that it is kind of a nice, right? Polyhedra, collection of polyhedron, is the following. Classical, very important notion in tropical geometry that we have already seen anyway. So given a polynomial, usually some kind of Laurent polynomial, remember Laurent polynomial just means you have x and x inverse. Yeah. And we have multiple variables here, and it's whatever. I just denote that as follows. If you have x1, x2, and they have some exponents, whatever, 3 and 2, I can just denote the exponent as 3, 2, right? As a vector in this case, z squared. Right? I allow negative powers, so that's what the notation here means. I just have some coefficients, and I have such exponents, and I have one of those polynomials. And you literally just take the exponents, you put the points in the plane, or in whatever type of space it lives, if it's higher dimensional, and take the convex hull, and it's usually called the Newton polytop of your given polygon. Sorry, not polygon, but of your given polynomial. And it's a very important notion in algebraic geometry and tropical geometry. So here's our Newton polytop, 2, 3. So let's write it down. Newton polytop of this polynomial here. Let's write it down. 2, 3 is the first one. Then 1, 2 is the next one. Then 2, 2 is the next one. 2, 2. And then 3, 1 is the last one. 3, 1. And so let's try to find all of these. 2, 3, 2, 3. This is our first point here. And then 1, 2, 1, 2. This is our second point here. 2, 2. 2, 2 is the one in the middle, and the final one can only be 3, 1, and of course that one. And yeah, the Newton polygon is then the the yellow area, right? So the yellow polygon polytop, right? So that's a very important notion in algebraic geometry, and moreover in tropical geometry, because tropical geometry really cares about the exponents. I hope this is clear at this point. It's kind of a log of geometry, so you take the log and you really care about the exponents, and this is a natural geometric object you will associate to a tropical variety. Standard object in polyhedral geometry, standard object in tropical geometry, so the two should be reasonably closely related, right? Hope that makes some sense. And tropical varieties themselves form polyhedral complexes. That's the whole point. In this case, the polyhedral is very boring. It's a collection of lines and rays. I said again, here we really need that the polyhedral could be unbounded. It could be a line, right? A polygon would be the it could be a ray. A polygon would be the line. So here you have 2 lines, and how many rays? 5 rays, and they form together polyhedral complex. So a tropical variety is a polyhedral complex. The main invariant or geometric notion associated to a tropical variety is the Newton polygon, is also some polyhedra. So that's where polyhedral geometry and tropical geometry really start going hand in hand, and we are going to explore that further. Anyway, I hope you enjoyed this video, and I also hope to see you next time.